Neurips 2024, part 5. This is a paper, Dhruv, Batra and all from Georgia Tech, talking about pre-trained text to image diffusion models and how versatile they are for downstream control. So the goal is the following. Like, you have a robot, and the robot has to navigate in nature and do fine-grained tasks, pick up stuff, put something somewhere, that kind of thing. And the question now is, how do you represent nature and have the robot do stuff? And there's a couple of attempts and directions that the community is going. In particular, since the rise of the foundation models, the idea has come up to use language and combine it somehow with image and then have the robot move around. So in other words, why do we have to learn to see and interpret nature from scratch when we have language that helps us with semantic understanding? Do I have to learn what a door is in an end-to-end, no prior type learning environment, or can I add something to the image saying, well, this is a door? And with that, I can use the power of large language models and their semantic understanding, what a door is, that the door can be opened, that you can walk through a door, all that kind of knowledge can be used. In other words, if you take vision language models, which is what these models are called in a sort of general way, so vision and language, they are basically vision models with priors. And I abide to the saying that priors are just learning data in disguise, which is true. What is a language model? It has been trained somewhere else, let's say in GPT or Grok or Llama, to extract knowledge from text. Now, that's a prior that we can use together with image, and then we know that a door is a door, whatever that is. We know it when we see it. And we can formulate it. And we can use language to express concepts, pretty complex. There's a bee on a flower. That's a compressed knowledge. For example, that means it's spring. That means this flower is blossoming. There is probably honey somewhere. We are definitely not in a desert, right? So there's so much knowledge you can extract from one sentence. And for us humans, of course, that's like, duh. So what's the big deal? Well, think about a robot that doesn't know, the thing doesn't know anything. And you want to teach that robot something. And the question is, how do you do that? Now, there's the Richard Sutton / I would say Berkeley crowd that, and probably even Stanford, basically the West Coast people that are saying, let's get rid of all the priors and just train. Now, Shuren Song, for example, is not in that camp. She's at Stanford. So I don't want to put everybody in the same boat. I would say Dorsa Sadig also is I would say, a big fan of priors, just given a recent panel I attended at Coral. But anyway, I think in general, what I'm saying is, let's take Sutton's, the bitter lesson. Lots of data and general models. Let's not put priors in there. Now, what Batra and et al. Are doing here is saying, okay, fine, look, we have access to models, we have access to priors. In other words, we have access to language models. How can we use them more appropriately? So this is the question here. And the answer is, there is one model that is pretty, popular, and that is CLIP, which is a contrastive model which trains data on this is a cat, this is not a cat, this is a door, this is not a door, that kind of thing, and gets pretty good at labeling, auto-labeling images. So you can run an image, use CLIP, and segment the image, and then have the robot do stuff. So you can take an image of your kitchen, and then segment the kitchen into cutlery, plates, flowers, etc. And then the robot can do stuff. And what, according to the paper, has been shown in the research is that CLIP is not really good at fine-grained tasks. So I guess the way I understand this is It's pretty good at understanding that a flower is not a plate and a plate is not a cup, but picking up the cup and not destroying the flower while you're doing that, that's relatively difficult using clip alone. And therefore, what Batra et al. Are doing is using something else, which is a diffusion model, and really tweaking the diffusion model in a sense that what we're doing here is, denoising an image towards something that we understand, right? We put noise on an image and then train it in a way that we denoise it and therefore have a representation of reality or what we see, and that can be useful. Now, what they're doing is they're doing really two things here in this paper. One is they're trying to work on the denoising design, things like time steps, things like concatenating several layers of the denoising intermediate features. And then they're also looking at the cross-attention between the image and the text. So there's two, I would say, big picture design choices that they're looking at. And like every other good research paper, they're coming up with a hypothesis, they're training, they're using different evaluations, different type of level of tasks, and they're comparing it with existing data sets and existing research. And most importantly, I think what I always find interesting is they do some sort of ablation study where they try to really analyze, okay, we are better in certain things. For example, in this paper, they realized that in certain tasks, particularly when fine-grained control is important. So when the robot has to do this, thread a needle type of task, it is really good to have denoised diffusion models. You have diffusion models with text representations of reality, and use that as a control mechanism for the robot. And the question is, why is that, right? Now, I don't want to get too philosophical here, but I think fundamentally what they're coming up here is not too surprising, which is that if you really carefully design the diffusion model, you will get better representations of the image world that you're seeing. And then if you concatenate it properly with text, you can probably get more semantics out of your understanding. So the human equivalent would be, if you walk around the city, you can segment the city in buildings versus streets versus people, but you can also segment the city into shops and stores and pizza parlors and clothing stores. You see, the more fine-grained you get, the more useful your representation is for downstream tasks. If you're hungry, you will certainly want to have a more fine-grained representation of what you're seeing. But then, how fine-grained do you want to go, right? Do you want to understand the level of the quality of the bricks per building? That's probably useful if you want to blow up a building or something like that, but not if you want to buy pizza. So I guess the conclusion of this paper, in my opinion, is that it's task dependent. So we are still in the early stages of foundation models for robotics, and we are still in this bespoke world where certain approaches are better for certain tasks. Like I just used, I think my example with the city really hits the nail on the head here. Like, how much fine-grained understanding do I need of the city, and how much concatenation with text do I need? So this pizza is good, this pizza isn't good. Pizza is an Italian dish that, so how much semantic understanding do I need? And I guess we're always coming back to the same question, which is, well, ideally, we just want to learn everything about the city, put everything in a gigantic model, use an appropriate transformer-based model, and then extract that knowledge to fine-tuning, and then we don't need all these priors. So if we had billions and billions of epochs of walking through a city, we would learn what a pizza is without having to rely on language models. We will learn that this pizza is better than that pizza based on maybe the way it looks or the way the lines are or the price or whatever. And I think that's the one side of the coin. The other side of the coin, in my opinion, is, well, okay, look, we already have knowledge. Like text knowledge is real knowledge. It's pre-trained and useful. So why don't we use it? I think that's kind of the world we live in here. I want to tie this paper now to our more immediate use cases that we were living in here at Orange Capital Partners, to remind people why we're doing these paper discussions in the first place is, of course, we're in the business of wealth creation. We are looking for fundamentally new concepts and engineering practices to create wealth. So we start with science, we look for tech, and then we look for the entrepreneurs that can transform that science into products and services that create wealth. And for us right now, our largest positions are in NVIDIA and Tesla, and both of those positions are morphing more and more into robotics bets on robotics in a very large sense. So, for example, Omniverse is a platform for 3D representations that NVIDIA is building, which will eventually help robotics. Tesla is building Optimus and has already a robot in the form of a car, Cybercab, things like that. So in both cases, the question now is, okay, how does this particular paper, does it help us or not? And I think I want to really be very clear about this for listeners. And I think, long-time listeners know that this is not investment advice by any means. The purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. That's what we're doing here. So please take this as an inspiration for how we approach things. Do it your own way. Definitely do your own research. There's no stock recommendation here or anything like that. All we're saying is, look, this is the kind of work that is being done in academia right now. Now, we don't know what Tesla is doing. We know a little bit more what NVIDIA is doing. And NVIDIA is definitely in that camp of let's use as much data as we can and train on as much data as we can and as general models as we can, because that's also what NVIDIA is really good at. With Omniverse and CUDA and its parallelization machine, they can train more and more multidimensional data sets and hopefully get to a point where the representation of reality end-to-end trained with no priors and the one with priors sort of converges to one gigantic representation of reality. That's where we're going, where we could have, let's say, a virtual version of a robot picking up stuff in a kitchen and then do a sim to real that is relatively straightforward, and then build real robots that can do that. That's the holy grail. We're not there, but that's where we're going at. We believe that the wealth creation for that is in the trillions, and therefore it's worth our time. To summarize, this paper by the way, just as a tangent, the paper selection, maybe I should do an episode just about the paper selection. The paper selection here is pretty crude. We're just looking at papers from people that we know. So Dhruv is somebody I know personally. I've spoken to him a couple of times. I wouldn't call ourselves acquaintances or friends or anything like that, but I know him. We've spoken, and he's one of those academics that I think I could have a beer with and chat about his work and also just generally the world. In other words, he's a thinker. He's not just a nerd engineer. And he certainly doesn't have that veil of arrogance and elitism that comes, unfortunately, with a lot of these academics, particularly from the so-called elite universities, which he is part of. Now, having said that, again, the goal in our paper selections is to go with those names, and then maybe we'll do a final round and go through maybe best paper and things like that. Neurips is doing a good job in filtering all that stuff. That's the value added that we see from Neurips, that they filter a lot of interesting work that we can then use. And this is one of them. And again, the idea is really look at what's being done in science. And in this case, what science is doing is really try to understand where is the sort of the sweet spot in the Venn diagram between end-to-end no priors versus priors, and the answer is, well, we want to have priors in form of language. Now, how do we train? We can train with diffusion models because they're a little bit more fine-grained and they're sequential, if you will, right? They're sequential. You're denoising steps, versus contrast is more crude. It's a cat or not a rat. So with the sequential nature of diffusion models, maybe we can have more fine-grained results, and the answer is yes for the specific tasks that require that. And I recall the city example that I used. And I think just again, to just bring the point home, the two design choices that robotics people can make right now in representing reality, one is first we want to use a diffusion model. I think that's definitely coming across in this paper. And then we can design the diffusion model in such ways that we want to, fine tune the granularity of the time steps and the latent concatenation of the feature space, things along those lines. In other words, we want to have different. How much granularity do we need? Do we need to understand the level of the bricks, or is it enough to know that there's a pizza parlor in the building? Is it enough to know that this is an apartment building? How much granularity do we want? And then how much semantic knowledge do we want to attach? In other words, how much text do we want to attach? And I think they're doing a very good job in doing that research, bringing up the questions, and then also the results are sort of expected, which is depending on the task. The more granularity and the more semantic understanding we have, the better if the task requires that. And sometimes the task doesn't require that. If all I have to do is, let's say, find a hotel in a city, then I don't need to understand the level of quality of the pizza parlors in the city. All I need to know is the difference between hotel and not hotel. So CLIP might be enough. But if I want to understand a hotel in a good neighborhood with nice rooms and nice views, I need to understand more, and then maybe something like a representation a la diffusion with appropriate concatenation with text is more useful. Thank you.